Hi, class. Here's a little mini lecture about topics 1 through, well, here I'm just gonna, this is topic 1. So this little set of notes here have topic 1, 2, and 3. Um, Here I'm just gonna talk about preliminaries first, and then we'll talk a little bit about groups. And that's it for this one. So they'll get a little bit bigger as we go. There's a lot of stuff in the preliminary section. So I'll just sort of go through this stuff sort of quickly, and then we'll talk more about this in class when we meet. The sets, I'm going to assume you basically know what sets are, what functions are, and here I'm really just sort of introducing some notation. Let me just make sure we have a couple of things straight. So first of all, let me do cross products first. So if A and B are sets, A cross B is the set of all pairs AB, where A is in A and B is in B. Whoops. You're gonna have to get used to my bad handwriting, sorry. So that's pretty simple, and we can even view this like a Cartesian plane. We can sort of, now there's no ordering to these things, right? So I'm drawing it like there is an ordering, but there's not. All right, and we could have like a point A here and a point B here. This is a useful way of thinking about it sometimes. So we have the point AB, right? And then of course we can do products of more than two sets, and you can even visualize this as a cube type thing, right? But then if we do more and more, then you want to stop visualizing it, but you still have the basic idea. And we can do a bunch of them like this. Do even an infinite set, right? So this would be the set of all. Now here we actually would have functions going from I to the union of all these things. With the property that f of I is in a I, right? And so, so one thing here is we can view this as a function going from, sort of 2, going from like 0, 1 to A union B, right? Where, f of 0, 0 is in A, and f of 1 is in B. Maybe I should have started counting at 1. We're talking about set theory, so I'll explain why I'm not starting at 1, but this could be 1 and 2 instead of 0 and 1, right? That's one way of coding an ordered pair, right, in terms of sets. Anyway, this, to some extent, this should be review. I mean, cross products like this should certainly be review. This might be a little bit new, and actually, even there's something even a little bit subtle here. Even to say this is non-empty, when this is an infinite set here, right, requires a set theoretic axiom called the axiom of choice. So we are getting into a little bit of set theory when we start using these things, but we have to use them all the time in algebra. Oops, axiom, not axioms, axiom of choice. In fact, whoops, saying this is always non-empty when these are always non-empty is actually equivalent to this thing called the axiom of choice. And that's sometimes abbreviated AC, and we won't really use it much in this class, but it comes up now and then. You actually use it in linear algebra too to show that every vector space has a basis. So it's one of those things mathematicians use all the time, and it's sort of a hot philosophical topic, or was anyway. Something mathematicians still debate whether or not it's true or false, but anyway, it's something you typically just use. Anyway, just to make sure we're clear, functions, right, are contained in A cross B. So I have f, the notation would be f, a function from A to B, right? Then as a set, it would be a subset of A cross B, and you might view that as a relation, right, a set of ordered pairs, with some properties, namely that for all A and A, there exists let's see, exactly one B and B, such that f of A equals B. So there can't be any question about where you're sending A, right? Now, lots of things might get sent to the same B. That's not a problem, and so if that if for every b there's just one a, such that f of a equals b, then we say the function's 1-to-1 or injective. If every b comes from some a, we say it's onto or surjective, right? And if it's 1-to-1 and onto, it's bijective, and in that case, it would have an inverse function. So, all this sort of stuff you teach algebra students usually when they're learning about logarithms, because we define the logarithm as the inverse of the exponential, and so we have to go through all this stuff, right? One thing to note here is that when we write this notation, we really mean this is the domain. So we're sloppy about that in calculus sometimes, right? Like sometimes we say let f of x equal the square root of x function, and sort of think of f as a function from r to r, but it's not, right? It's actually a function. This is wrong, right? It's actually a function from 0 infinity right to the reals. Now the domain can be a subset of this set over here, right? So this is called the co-domain sometimes, right? Sorry, I mean the range, right? The co-domain is this B, and the range would be things that are actually hit by something in A, so that would be a subset of this B. And this kind of notation should be clear too, right? Sometimes we draw these things, like that, right? F, So anyway, I don't want to spend a lot of time on this because should be pretty basic. Few notations. So F inverse of A, right? So let's see. Let's be a little bit careful here. So let's say I have a function. In fact, I could even do this for relations, but I'll just do it with functions because that's our main thing here. So let's say I have a function going from x to y. So these are sets, right? And I have A, which is a subset of y now. Whoops, sorry. A, a subset of y. Then F inverse of A is actually going to be the set of all x, such that f of x maps into A, right? So things that map into A, right? And that defines this sort of f inverse function is actually a function from the power set of y, that's the collection of all subsets of y, into the power set of x, collection of all subsets of x. Okay, so this is defined for any subset of y, even if y isn't the range, right? Could be the empty set, right? So that's a possibility, but this is really just a matter of notation. So the thing I'm defining is this symbol here, f inverse of A. Also, we use this. Now, this symbol gets overloaded for lots of things. So when I have two sets, right? Suppose I actually have, these are in an algebraic structure, right? So I have an kind of addition, right? That's defined on objects in these sets. Then when I write A plus B, I really mean the set of all A plus B, where A is in A and B is in B. And we'll use this notation all the time, particularly in this kind of form, G plus, some n, right? So this is a fixed element, and that's a set of elements. So this is really the set of all G plus n, where n is in n. Okay, so this is really just notation here, right? So I have a set plus a set. I don't mean anything sort of strange algebraically with sets. I just mean the set of all the elements from A, B added together, right? If I have a single element plus a set, I mean G plus anything in that set in, right? So this is just notation. Same thing with AB, right? AB would be the set of all AB, right? Such that A is in A and B is in B. And similarly, GB, right, would be the set of all GB, such that B is in B, right? So just as above, right? In fact, in some sense, I shouldn't even write that as two separate things. I should say if I have a binary relation, that's defined here, then I could define A, say a binary relation star B, right, would be the set of all A star B, where A is in A and B is in B, right? And so this is sort of the kind of thing we do with group theory. We have these generalized kind of algebraic structures, and this can be composition or addition or multiplication or whatever it is, right? Some sort of binary relation. Let's see. So I don't want to say much more about sets right now. We'll use this sort of notation all the time. So if you have questions about the notation or about sets, ask when when the questions come up, right? So part of your job is to ask questions. I do want to go on and look at induction and look at a couple of examples, and I'll probably split off a separate little video for the number theory, because I can only make these 30 minutes each. So let me just clear all this, because I don't really need this. Okay. So induction is a really important fact about the natural numbers. Oh, one thing I was going to say about sets, because I might use this notation along the way here. We tend in math to view the set of numbers less than a number. So these, when I'm talking about numbers here, I mean whole numbers, or actually natural numbers, right? So these are the numbers 0, 1, 2, and I do put 0 in here, and you should put 0 in there, but there is, some people don't. So, 2 would be the set of all n and n, where n is less than 2. And I guess you should have looked at something like this in Math 509, right? But it's kind of useful, right? Because then I can define like, x to the 2, right, would be the set of all functions from 2, to x. And now what does it mean to have a function from 2 to x? Well, it means a function from, what is 2? Well, it's just 0, 1, to x. Right, so this just turns out to be useful notation. So when I do things over the natural numbers, often I view those natural numbers as these kind of sets. So just sort of keep that in mind if I happen to use it. Okay, so there are these three things. There's induction, least member principle, and well ordering principle. And I guess in some sense, least member principle and well ordering principle are the same. So maybe I'll sort of consider these to be the same. And there's kind of strong and weak induction, right? So there's sort of a whole litany of things to talk about. So let me quickly do a definition, and then let me take a really simple example and sort of prove it in a variety of ways. Okay, so that you can see and then then when I do the number theory, or maybe even here, I'll do an example which is not so simple, that highlights things a little bit better. So let's see. So there's kind of different forms of induction. And once you sort of realize that all these are the same, often you'll just say, oh, by induction, or by, well ordering, or by minimal member principle, or something like that. They all mean the same thing. So weak induction looks like this. You have a base case. So you have some A, which is in Z. So this is always, this is not always something about the integers or about the natural numbers, but usually in our case, it will be. There's other well-ordered sets, but that's more for a set theory class. Maybe for topology too. 571, maybe, right? Okay, so there's some fixed thing here. This will be like the base, okay? And we're going to say we have some property that holds at A. So P of A holds whatever P is, right? And so we'll have an example in a minute. So we say so when you're doing an induction proof, you want to prove this. So you want to prove this. Prove the base case, right? And then you're going to prove that, you're going to prove this. You're going to say if P of N holds for N greater than A, so maybe let me just write it like that. I'll write this out formally in just a minute. So for N greater than A, or greater than equal to A actually, P of N implies P of N plus 1. So again, this you have to prove, right? So this is your job, right? You prove that, right? This is so you don't prove it, you just pick an arbitrary n, not your favorite n, arbitrary n, right? And you prove this implication for an arbitrary n. Then by induction, you get to just get something for free by induction. You get that for all n greater than or equal to A, P of n holds. All right, so this is the way it's used. So, there's kind of a picture that's common. There's probably lots of pictures, but like, okay, if I can make it up onto the first ladder, rung of this ladder, right? And given that I can make it to the nth rung, I can always make it to the n plus first rung, right? Well, then I can reach any rung, right? That's kind of what it's saying, right? So that's kind of what induction says. And why is this weak induction? It's weak induction because we're just going from n to n plus 1, okay? So what is strong induction? So strong induction looks basically the same, except you have a slightly different induction hypothesis you prove. And this is important. We'll see an example where this is important. Not the first example, but a later example. So here you have a base case again. So you still have to prove P of A. In fact, you might even have a lot of base cases, but I'll just pretend we had one. P of A base case. I mean, there are cases where you need like, I don't know, 5 base cases or something. So you prove individually that those 5 cases happen, and then you start proving it by induction on up there. But what you prove then is you prove that for all m, you suppose for all m less than n, P of m holds. And I gotta be careful. Yeah, I mean, I gotta start with my base. For all m greater than or equal to a. Well, okay, let me make this for all m greater than or equal to a less than n, P of m holds. So this is an assumption. This is your assume. All right, then you have to prove that P of n holds, right? So this is for all m less than n, then we got to prove P of n holds, okay? So this is a common way of using induction, and usually the point here is there's no way of going from case n to n plus 1. You got to say, I have 2 things below n, and I need to go up to some bigger case. I mean, we'll do this more formally in a minute, but suppose I'm going to prove something about integers and multiplication, and I have the n, factors into some k times s, where these are smaller, right? So it's a non-prime, right? And then so these are 2 things that are smaller, and maybe there's some property I have about k and s, and I want to prove that it holds it in, but I can't get from n plus 1 or n to n plus 1 here. I need to get from these 2 factors up to n, right? So, and you don't really have any control over what those 2 factors might be. So that's sort of a typical case where you use strong induction. And you use it for lots of, I mean, like if I want to prove things for trees, right? You sort of prove things for levels of trees. I mean, so there's lots of things you use induction for. Okay, so the minimum member principle or well-ordering principles like this, and I'll sort of draw a picture here. So suppose we draw Z, right, like this. Now Z, of course, isn't solid like this. It's individual things, like that. Right, so maybe here's 0, -1, -2, 1, 2, etc. Okay, so suppose I have some subset of Z, right? So I have some subset of Z, let's say A, right? And I want to say A is bounded, right? So I have that there's some A less than A, okay, or even less than or equal to A. But of course, if I'm less than, I can subtract 1 and be less than. So here I'm using that notation, right? So I mean that A is less than everything in big A, right? So I mean A is less than or equal to X for all X in A. So that's what this kind of notation means. So this would be a lower bound of A. It's not necessarily in the set A, right? Then the minimal member principle says there exists, like an A star. So this is like an optimal one, right? So an A star in A, right? Such that A star is less than or equal to A. So in other words, there's a minimal member, right? So that's the minimal member principle. It seems obvious, right? I mean, you can't, if it's bounded here, I can't sort of go backwards infinitely often above this point. Okay. That's actually another equivalent here too that I should add to the notes. I'll try to remember to do that. In fact, I'll pause and just add that right now. Okay, so I think I'm back. So yeah, so I just put an or here between these 2 things, which are essentially the same. And there's also this infinite descent, right? So it just says, starting from some point in Z, which is bounded. Maybe I shouldn't use A here. Let's call this B. So let's say I have a bounded set above A again. So I'm just interested in some subset like this. I can't bounce infinitely far back, infinitely many times and stay above a lower bound. All right. Now, of course, you can go infinitely far back in Z if you don't have the bound, right? Because you can go off to minus infinity, right? But if there's a bound, you can't go infinitely far down. Okay, so we'll use this kind of argument quite a bit. So that's kind of the theory. Again, I'm assuming you've seen. I mean, this is preliminaries, and this is stuff you should already know, but maybe have forgotten or it's been a while. Let me give a really simple example. And first, let me prove this. So I'm going to show that summation I equals, let's say 1 to n, all right, is equal to, and I think it's n times n plus 1 over 2, but let's just verify that in a non-inductive proof, kind of a non-inductive proof. So I'm going to write down here 1 plus 2 plus 3. This is like, apparently Gauss did this to upset some math teacher. So it goes in a quarter and add up the numbers 1 to 100, and he came back a few seconds later, and there was, I don't know. This was known a long time before Gauss, of course. So here I'll start backwards, n minus 1 dot plus 1, right? So I'm just sort of flip the sequence around. I want to know the sum, right? That's what this is. Here it is again. So I add these together, so I end up with 2s down here. And over here, when I add these, I have n plus 1, right? Because n and 1, n minus 1 and 2 is still n plus 1. Okay, n plus 1, right? How many of these are there? Well, there's n of these, right? So this is n times n plus 1. And, I divide by 2 and I get s, right? So that's the correct formula. By the way, formally, when we have dot, dot, dot like this, there really is an induction here. I mean, almost always there's really an induction going on, right? Here it looks like there's not, but there really is. But anyway, let's prove this by induction, and let's do it in all these different ways, and I've got 8 minutes to finish this. So let's see, weak induction. Okay, so first, so the base case will be 1. Whoops, sorry, I just moved my screen. N equals 1. Okay, so that is summation I equals 1 to 1 of I, which is, summation of 1, right, is equal to 1 times 1 plus 1 over 2. And of course, that's 2 over 2, which is 1, right? So the base case is good, right? So at n equals 1, the thing holds. Okay, let's assume that that summation I equals 1 to n of I equals n times n plus 1 over 2. Okay, well, let's compute I equals 1 to n plus 1 of I, right? And so, of course, this is summation I equals 1 to n of I plus 1. Sorry, n plus 1. I'm just pulling off, one of the indices up here, right? And so by assumption, this is n times n plus 1 over 2 plus n plus 1. Okay, and you can play with this a little bit. Well, I'll just say you can play with this a little bit and see that this is n plus 1 times n plus 2. I'll leave this as an exercise. It's kind of trivial, over 2. Okay, so we assumed Pn, and we proved, summation I equals 1 to n plus 1 of I Pn plus 1. Right, so we could say by induction, induction, for all n greater than or equal to 1, summation I equals 1 to n, I equals n times n plus 1 over 2. Okay, this is like one of the typical first examples of induction, really simple example. In this case, you can clearly use strong induction, right? So the base case is the same. So the assumption then would be for all m less than n, right? Summation I equals 1 to m of I equals m times m plus 1 over 2, right? And now I want to prove that summation I equals 1 to n I equals n times n plus 1 over 2. And of course, here what you do is you just drop back to n minus 1, right? So you say, well, this is equal to summation I equals 1 to n minus 1 of I plus n, right? And now it's just the same argument. So now this, by assumption, right, we have that this is n minus 1 times n minus 1 plus 1, so that's n over 2 plus n, right? And again, you do the same algebra, and you get that this is n times n plus 1 over 2. Okay, so there it is with strong induction. I'm going to do another more interesting example in the number theory case. In fact, a couple of interesting examples. If I want to use the minimal member principle, right, I can say, let's see, usually this is by contradiction. So suppose that, let's see, suppose A equals the set of all n such that summation I equals 1 to n of I does not equal n times n plus 1 over 2 is non-empty, right? So there, we can do that. In fact, the set of n greater, let's see, greater than or equal to 1, right? Because I do want to put a bound on this, right? So we have that 1 is less than or equal to a. Remember that was our base case above, right? Now I can show that 1 is not an element of a, right? Because we know that for 1 this actually holds. I'm assuming this is non-empty, right? So let k and a be minimal. Well, what does that mean? It means that k minus 1 does satisfy what we're trying to prove. I mean, without the not symbol there. But then, of course, we just run the same induction proof above, that, the same proof I had above that would get me from k minus 1 to k, and so that would show that k is not an a, and then we'd have a contradiction, right? So, so I'm not writing everything down because it's like same argument as above, shows that, p, the thing I'm trying to prove at k minus 1 implies pk, because we did that argument, right? So we get a contradiction. We get k is not an a because it actually does hold, right? But the assumption was that k was the least thing in a, so right, so we have a contradiction. So that's kind of, this kind of proof by contradiction is clearly related to the induction, right? So that kind of shows you how the minimal member principle and induction are equivalent. Because here you're proving something by contradiction with the least member. Up there you're trying to get from one thing to the next, and they're really just kind of opposites of each other in that way. Let's see, I'm down to 2 minutes, so let me try to do an infinite descent, right? So suppose that summation I equals 1 to n of I does not equal n times n plus 1 over 2, right? Well, then summation I equals 1 to n minus 1 of I does not equal n minus 1 times n minus 1, plus 1 over 2. Because if it did, we would have the same argument that would get us, if this was an equality, we would be able to get that equality, just as before, right? No difference again, right? So I have that not p of n implies not p of n minus 1, right? And I can just keep running that argument, get this descending sequence n minus 1, n minus 2, etc. That keeps going down like this, right? I'm only interested in n's bigger than 1, and of course we know that p of 1 actually holds. So it'd have this infinite descending chain above 1, and that can't happen, right, by the infinite descent thing. So all these are sort of equivalent to each other, but that's basically how you do. You can prove this thing using any of those properties. It's good exercise. We'll do a lot of induction-like proofs in the class, and I'll give you a more interesting one when we do the number theory video. Just a second. Okay, so I'll see you in the next video.